Petronella Nel is Senior Lecturer at the Grimwade Centre of the University of Melbourne and leads a collaborative ARC linkage project, a national framework for managing malignant plastics in museum collections. She is interested in developing analytical techniques for characterizing materials in order to inform their preservations. Welcome, Petronella Nel.
Okay, so I'd like to thank the organising committee for the opportunity to present to you my journey with identifying polymers over the past 15 years. This is the exterior of the Grimwade Centre's purpose-built laboratories at the University of Melbourne, which we moved into in 2015 and where I teach and do research into materials conservation, with the majority having involved identifying and characterising polymers, which I will discuss with you today. In summary, I will discuss a review of the literature that specifically discusses polymer identification. Then I will provide a brief history of technological developments in infrared spectroscopy, and then I will share my experiences with polymer identification. And for some fun, we will look at a few objects and guess what they are made of. So for the literature review, I searched the AATA online database for the terms identification and plastics and identification and polymers. My focus was on the development of thinking within the materials conservation discipline. My aim is to use this exercise to guide conservators towards information that will be helpful in progressing their knowledge on this issue, but also provide context to the interesting papers that will be presented at this meeting. One of the earliest materials conservation texts on this topic is an article by Sharon Blank, which appeared in Studies in Conservation. A small section discussed the identification of plastics and outlines what I believe to be the main strategies used in materials conservation to identify plastics. It starts off with the simple non-destructive methods such as observation and contextual information. Then there are the destruction methods that centre around physical, burn and chemical spot tests, and then instrumental methods which focus on infrared spectroscopy. 9 references were found to specifically address the topic of polymer identification. The light grey question marks indicate where the topic is mentioned, but little detail is provided. As you can see, over time, all 5 categories are being recommended depending on the perspective of the authors. First, there is the 1991 book by John Morgan. Then in 93, there's the article by Helen Coxon as part of the proceedings of the 1991 Saving the 20th Century meeting organised by the Canadian Conservation Institute. Then there is a spinach leaflet produced by Williams et al. Titled Guide to the Identification of Common Clear Plastic Films. Next is the book edited by Quay and Williamson, where a chapter focuses with 2 parts on first the perspective of Colin Williamson, who belonged to the Plastics Historical Society in London, and he focused on simple analysis methods. And then there is the second part by Thea van Oosten, a conservation scientist from the Netherlands, focusing on analytical methods. Then there is a brief section by Karen Koopman on methods to identify polymers, which was part of the Modern R2 Cares meeting in Amsterdam. The next one is the 2008 book by Shashua, which also has an individual chapter on the topic. And then there's a Conservagram article on the care and identification of objects made from plastic, which has a very good summary table of simple non-destructive methods at the end. And then in 2012, there is the Pop Art publication, which had 4 main themes, of which the first was identification and characterization of plastic artifacts, which contains 7 articles. And finally, there is a 2018 Canadian Conservation online resource, Caring for Plastics and Rubbers, created by Fenn and Williams, which has a table containing common trade names, common occurrences in collections, a small section on plastic identification, and a table listing the most useful chemical spot tests. Okay, so now we will look at more detail at how these references address the 5 categories of polymer identification. So with observation, common themes are appearance, colour, odour, feel, hardness, and degradation characteristics. The references that are particularly good at providing reasonably detailed information is Morgan, Coxon, Williamson, Zephyr, and Fenn and Williams. However, 2 websites that I would strongly recommend is the MODIP website and the RCE Plastic Identification Tool website. And I believe you will be hearing about interesting developments in this area during the conference. With context, the common themes are reference literature, date and method of manufacture, trade, names, designs, and function. The references are particularly good at providing reasonably detailed information, and these are Morgan, Williamson's section, Zephyr, and then again the Fenn and Williams website. And I will again direct people to the MODIP and RCE websites for information regarding acronyms, development dates, trade names, manufacturing processes, and typical uses, as well as history, production, and application. Now I'm going to move on to the simple destructive tests like density, solubility, the hot probe, and the burn tests. Generally, these tests are not recommended due to occupational health and safety and ethical issues. The hot probe test basically allows you to categorize whether the polymer is thermoplastic because it melts or thermosetting because it chars. These tests tend to be based on literature from the 1960s to the 1980s, and I was able to find a flow chart published in the Plastics and Chemicals Industries Association, which was published in Australia. And this is summarised on the next slide and is useful at providing an overall perspective on these tests. So this is the flow chart published in the particular book of that association. And it involves, first of all, determining whether the plastic melts or chars, then a comparison with the density of water, separates the thermoplastics into 2 more categories, and then the response to burn tests potentially allows differentiation between various polymers based upon the subjective interpretation of flame colour, odour, etc. With chemical spot tests, again, you have occupational health and safety and ethical issues. The Bilstein and diphenylamine test are most commonly recommended for identifying chloride and cellulose nitrate-based polymers, respectively. A document created by Remillard from the Conservation Centre in Quebec, titled Identification of Plastics and Elastomers, Miniaturized Tests, comprehensively summarises the various options and provides good visual guidance on how to do the miniaturized tests. Many of these are also summarised in Odegaard et al.'s book. However, these tests tend to be based on old chemical literature, as shown in the next slide. So this is an overview of a 1944 article by Shaw, which appears to draw on all of the destructive tests, like the physical burn and chemical spot tests. However, chemists tend not to use these tests anymore due to technological developments of instrumentation, which I will discuss next. So in the conservation literature, instrumental methods are best summarised in the section by Weston in the Quay and Williamson publication, Joshua's book, the Pop Art book, and it should be observed that there's very good agreement between the literature that infrared is the best instrumental method for identifying a polymer. To learn more about infrared spectroscopy, I recommend referring to Derrick et al. And Stewart's book about infrared spectroscopy as being very approachable texts. I will now briefly review the history of infrared spectroscopy, which will blend into my own experiences with identifying polymers. When I was an undergraduate chemistry student in the late 80s, we measured infrared spectra on dispersive infrared instruments, where the spectrum was recorded on a chart recorder as a transmission spectrum, like the image here on this slide. The process involved sample preparation and measurement of the infrared spectrum, where both processes were very time-consuming. So on the dispersive instrument, it literally was scanning through each individual wave number over a period of, say, like 5 minutes. In the 1980s, infrared spectroscopy underwent a major advancement when it was combined with fast Fourier transformation and personal computers, resulting in instruments where an infrared spectrum could be captured in a matter of seconds. So the measurement of an infrared spectrum changed from a slow, time-consuming process to a very fast measurement, a matter of seconds. In the final year of my Bachelor of Science, I noticed that the teaching labs were testing a new instrument called FTIR. At the same time, there was also excitement within the forensics discipline with the development of infrared microscopy that could now measure the infrared spectrum of an individual fiber. However, it is noted by Tangol et al. That identification was dependent on compiling a good reference spectral database of known materials. I then went on to do my PhD and then later a master's in culture materials conservation, not knowing I would be revisiting infrared spectroscopy. So as part of my minor thesis research project with my conservation course, I investigated 6 vessels in the Cypriot pottery collection at the University of Melbourne. My aim was to use infrared spectroscopy to identify adhesives associated with the vessels. However, the laser at the School of Chemistry for that FTIR was broken and there were no other options. So I decided to make a comparison of visual observation, UV-induced visible fluorescence, solvent solubility, and chemical spot tests. In the literature, I found the following common adhesives were historically applied to archaeological pottery: cellulose nitrate, polyvinyl acetate, and acrylics. Whilst evaluating the chemical spot tests for their ability to identify the relevant adhesives, I came across what appeared to be a false positive when I analysed HMG B72, which is an acrylic, when the diphenylamine spot test came out to be positive. I was very concerned about this outcome, and I went to a lot of trouble to double check whether I had mixed up my samples. However, this test remained positive. So when I raised this issue at a conference, I was supported by a government organisation called the CSIRO to investigate this issue further, and ultimately proved that cellulose nitrate was added to what is supposed to be a conservation grade adhesive B72. However, there was a formulation change that occurred in 1995. Notably, I found several expensive high-tech techniques highlighted in red were not able to detect this formulation change. To me, this delayed detection of this potentially compromising formulation change indicated a need for more routine access to FTIR spectroscopy, monitoring and testing of materials. Here is the infrared spectrum of B72 before the 95 formulation change, and to the right is the infrared spectrum of B72 after 95 when cellulose nitrate was added. As you can see, this is definitely detectable using FTIR, which in comparison to other types of instrumentation is one of your cheaper options. At the time, I was using a traditional FTIR instrument and traditional sample preparation methods where the sample was ground up with potassium bromide and pressed into a disc. After attending a plastics workshop in 2005, delivered by Thea van Oosten in Australia, I became aware of a significant advancement in infrared spectroscopy, the introduction of attenuated total reflection, or the ATR sampling module, which removed the need for time-consuming sample preparation methods. The raw material no longer had to undergo any sample preparation and was simply pressed with a clamp against a highly refractive index crystal, and where these instruments had the ability to be mobile, with the travel or identify IR being one of the first of these instruments. I came across it when a sales rep brought it to the centre and demonstrated it to us. I asked him to analyse a sample we were struggling to identify. The sample was measured and then matched against their database, and a good match provided. This was the first time I saw infrared spectroscopy used in conjunction with a reference database, and I was impressed. The only problem I had with it was the diamond crystal was concave, leading to, if you were to say measure a sheet, having a significant indentation impressed onto it when analysed. So I was keeping my eyes open for a reflection sampling module with a flat ATR crystal. I found this with the Brooker Alpha FTIR instrument, which had a flat ATR module. I, in the first instance, rented the instrument from the company for about 1 to 2 weeks and used it to conduct a survey of the Cypriot pottery collection in the summer of 2009-2010. I used acetone-dampened cotton wool swabs to remove microsamples of adhesive from a vessel, which was then wiped over the flat diamond window. And with the evaporation of the solvent, this left a microfilm of adhesive from which an infrared spectrum was obtained. Each spectrum was immediately matched against the in-house database that was built using reference adhesive samples before we commenced the collection survey. If a spectrum was poor, this was immediately rectified. There was also a small number of samples that did not dissolve in the acetone. Some were found to be water soluble and were identified to be protein-based repairs. Another insoluble sample was needed to be manually removed using a scalpel blade and was compared to spectra on the commercial Polymer database, and from this polystyrene was identified, which was not previously reported to be found in archaeological pottery repairs. Whilst doing this survey, we also documented the visual appearance of the adhesive repairs and would guess what the identity would be before it was revealed by the instrument. As our eyes became more focused based upon identifications made by the instrument, we started to make good educated guesses, but every now and again we would be surprised where the eye had been fooled. It was found that 2/3 of this particular collection was repaired with cellulose nitrate, which is considered to only have a short lifespan in comparison to much better options. This is the unique ATR spectrum for cellulose nitrate, which has its own unique fingerprint. And as you will notice, unlike the previous spectrum I showed you where they used to present them as transmission spectra, in these more recent times, the discipline shifted to them being presented in absorbance mode. To identify the fingerprint of an unknown material, it was critical to have a spectral database of known polymeric materials, whether this comes from a commercial database or an in-house. In my case, the in-house was based upon my reference adhesive samples, as well as samples I obtained from the plastics workshop delivered by Thea van Oosten. It is also a good idea to verify the database spectral search match visually and check this against other reference spectra. So make sure it looks like a sensible match. Functional groups can be also identified by referring to correlation charts with two very good references that do a very good job of this is Socrates and Silverstein et al. A closer analysis of the cellulose nitrate adhesive spectra with specialist multivariate analysis software found that they separated into two clusters associated with the two accession periods of the collection. This was ultimately found to be due to a difference in the concentration of the dibutyl phthalate plasticizer containing either a roughly 2% or 15%, corresponding to the accession periods, and it also correlated with cellulose nitrate-based adhesive formulations. This was all verified using gas chromatography mass spectroscopy. However, what this ultimately demonstrated was that if you have collected good quality infrared spectra, these can later be reanalyzed and potentially reveal hidden chemical information about the adhesive formulation using FTIR spectroscopy, which is a reasonably inexpensive instrumental technique and reasonably inexpensive multivariate analysis software. A later survey of the Middle Eastern pottery collection by a PhD student, Emily Noak, further interrogated adhesive formulations to which cellulose nitrate had been added, with a third of repairs being found to be due to polyvinyl acetate, where cellulose nitrate was added to the formulation, most likely to the commercial product Yoo-Hoo All-Purpose. Around this time, we became aware of another significant advance with infrared spectroscopy. In addition to the internal reflection or ATR sampling modules, there are two other types of reflection referred to as specular and diffuse. Brooker provided a sample module option referred to as the external reflectance module, where no contact whatsoever is required with the sample, and where the infrared spectrum obtained is a combination of both specular, highly reflective, and diffuse reflection from matte surfaces, and this is essentially dependent on the type of surface you're analysing. An analysis of more recent infrared collection survey publications show that ATR and the external reflection modules are being viewed as the most promising for identifying plastics in collections. Saviello, in particular, provides a good set of reference data due to having measured reference samples from both Samco and resin kit. As I indicated previously, creating an in-house reference database is critical, which practically all of these references have done. In addition, I would just like to point out that the old methods of sample preparation have become now not used anymore. So in 2016, I was successful in obtaining funding that allowed me to collaborate with 4 universities and 6 museums located across 4 different cities. In 2017, we purchased the ATR-FTIR instrument with a diamond crystal. Now, this is the most expensive option, but with this crystal is essentially you can't damage it, which you can with some of the other options, so it is worth the cost. We also purchased a complete commercial reference database, and this suite of equipment was dedicated to the project. A year later, we purchased the external reflectance module. However, before progressing with making measurements, we were aware of the need to be able to compare data between the different project partners, and that the data will, in the long run, become accessible to the conservation profession and future researchers. So we had to do preparation work to optimise our processes before we rushed in and surveyed collections. So our standard FTIR data collection process, which I have here for the ATR module, is where we determined that the signal to noise ratio is optimized after about 32 co-added scans, and there was no point doing any more. We also had a process that we do before every single sample. So we always measure the background, and also just a little tip, if you want to minimize damaging your sample, you put a card on top in between the sample and the clamp to minimize any damage to the object. In terms of identification, we used the commercial and our in-house database. We made sure we verified our matches visually, we compared to the literature, and we also double-check with the spectroscopy specialists that are part of the project. In terms of our reference databases, we focused on the commercial ATR library, but there are things you can obtain from publications. We also purchased resin kit, however, it's only composed of modern thermoplastics. The commercial library was also had a focus on modern polymers. And so as a consequence, we paid quite a bit of attention to developing our in-house reference collection via the adhesives I already had, from workshops samples I had from Thea van Oosten and Yvonne Shashua. I then also purchased everyday plastics, went to antique stores to buy older plastics, and we were also able to purchase commercial sheets from polymer companies. Now, we did an evaluation of the performance of the ATR and the external reflectance modules, where we found we could easily identify all plastics in museum collections by using both these techniques in combination. It was found that the formaldehyde-based plastics were too hard to obtain good infrared spectra using the ATR module, and that these were better identified using the external reflectance module, which was very good at measuring their highly reflective surfaces. This is a spectrum we obtained for cellulose nitrate, where you can clearly see with the blue spectrum that it's best to be able to clamp the material onto the diamond window to achieve really good contact. However, if it's not possible, it can also be manually pressed against the diamond window to obtain a reasonably good quality spectrum. Alternatively, if the external reflectance module is used, no contact is required, and you simply, first of all, you would obtain this external reflectance spectrum, which doesn't really make sense. However, you can simply press a button and this performs a Kramers-Koenig transformation that changes this strange reflector spectrum into more familiar looking absorbance spectrum, which could then be matched against your reference database. I would recommend starting by learning how to use the ATR module and then later build up your expertise and then learn how to use the external reflectance module. Preliminary results from Museums Victoria found that these following polymers were commonly found in collections. So you can see it's the historical polymers. We also attempted to identify polymers from an archaeological dig site and found roughly 10 historic polymers consistent with the occupation period of the site. However, difficulties were encountered with odd shapes, hard plastics, degraded objects, and all of the objects being contaminated with soil. And for the details of this, this will be presented at the ICOM-CC conference that's coming up. Now, essentially, what has been shown for a long time is that there is a variety of limiting factors that may compromise the successful identification of polymers, whatever method of identification is used. First of all, there are the tests that can be subjective. Results can be compromised when the polymer is impure, which is most of the time with plastic collections, or when the polymer is degraded, which can be addressed by generating artificially aged polymer samples. Then there is the issue of the lack of art historical information, which is starting to be addressed by websites like MODIP and RCE. Next, there is the issue around where it has been flagged by publications, the need for training, and a lot of training workshops have popped up over time. Next, there was the issue of sample plastics, and a lot of reference kits are starting to turn up, like Samco resin kit, PIT kit, and the MODIP kit. And then there was also the issue around specialist conservators and conservation scientists. And my argument here is that we really need to train ourselves up, because this is a big problem. We need more people to become experienced. And a good starting point would be to, for instance, read the book written by a spectroscopy specialist like Shashua. In terms of an action plan that I would recommend you pursue if you do want to develop your professional development in this area is first access reference samples via kits that are available, or create your own. Develop observation and contextual terminologies by referring to references and the MODIP and RCE websites. And then try to see if you can obtain access to an infrared spec instrument. Ask the company to come and do a demonstration. Ask if you can rent it. And maybe over time, you'll be able to convince the people who hold the purse strings to purchase the instrument. Then create an in-house spectral database and start doing preliminary measurements and learn from your observations and the instrumentation. So I feel like you learn by having the interaction between what you see in a non-invasive way and the results the instrument gives you. And then I think it's really important for our discipline to share the information via databases and websites. It is hoped that research from this project will provide museums with information that will aid prioritising and effectively allocating resources for maximising the preservation and reducing the risks of this vulnerable group of cultural collections for future generations. A significant outcome is the provision of an accessible database where information can be shared to aid museum conservation efforts and facilitate future research. So all data created by this project is being migrated into a relational database, which will ultimately be made publicly accessible. It is also being used to visualize these large data sets and will allow us to draw connections, for instance, between data collected from different partner locations. We are collecting information about things such as condition reports, collection surveys, storage environments, and conservation treatments. And here we have had to develop controlled method vocabularies. However, it has been an iterative process where we have to come back and add new terminologies, but hopefully this is starting to be finalised. Here, with this particular visualisation, we can see the strong connection between polyvinyl chloride, the bright yellow, and plasticizer, the pink circle. And then it's also then connected to the dominant degradation factors for this particular polymer. Now we will quickly have a bit of fun with guessing the polymer identity of the following plastic objects. So this initial object, I will ask you to just very quickly for a moment think what that could be. And then here is this one, and think what that could be. In both cases, we're dealing with the imitation plastics where they're aiming to imitate ivory and tortoiseshell. And the match for the ivory was for cellulose nitrate, and for the tortoiseshell was cellulose acetate. And this additional object, which is sort of a pearlescent effect, that was ultimately identified to also be cellulose nitrate. Next, this object, for me, the clue here is in the colour, the design, as well as the use of a small travelling iron. So it has to be a polymer that is very resistant to temperature. And then this next object, it is hard and it's a bright white coloration. And on top of that, it had a trade name called Melmac. So the first one with the black was bakelite or phenol formaldehyde, and the white one was melamine formaldehyde, which relates to the Melmac trade name. And then this is just the spectrum for casein formaldehyde. As I've said previously, we found the external reflectance spectra to be more useful for differentiating between the formaldehydes. And just to be aware that at antique stores on the websites, all of these things will just be called bakelite. Next, this is what I was hoping was imitation ivory, and this is a good old Lego. So the spectrum for what I thought was imitation ivory ended up being polystyrene, which has this double peak here and this double peak here. And then the spectrum for the Lego is very similar, except for one of the major differences is this, the nitrile peak here in this middle section here. So a very subtle difference in this particular instance. Next, there is this pearlescent effect. And then this is, if you want to have a reference sample of nylon or polyamide, just get these cable ties. And so what the pearlescent effect was ultimately identified to be was not cellulose nitrate, but in fact, polymethyl methacrylate or perspex. For the polyamide, that is its unique spectrum, which I talk about as being that little stepladder thing. And then just another thing in this group is polycarbonate, and a very good reference sample of polycarbonate, if you need it, is just get your safety glasses. That's generally made of polycarbonate. So those are that. Okay, now the next thing is sometimes you think the label might be useful. And in this case, I ultimately found a reference book which had this particular object where they said it was polythene. Now, in both instances, the information was deceptive. The nylon string ultimately ended up being polypropylene, as well as the parfait goblet, which was from Tupperware, and Tupperware is cited on one of the references as well as being polyethylene based. However, this ended up being polypropylene. So that's just your polyolefins, and I just provided the polyethylene spectrum, although neither of the objects was comprised of that. And then next, there is just the spectra for polyvinyl chloride and polyurethane, just for you to see again the unique signatures. So based upon my analysis in this lecture, I would essentially have highlighted the books that I think are the most useful. They're highlighted in black. So there's the Cray and Williamson book, Yvonne Chashua's book, the Conservagram article, the Pop Art publication, the Canadian Conservation Institute online resource. And in addition, as I've indicated, you should refer to the MODIP and the RCE websites. Here is simply a summary of my identification references, with the ones highlighted in black being deemed to be the more useful. These are a summary of useful infrared spectroscopy references, again, those highlighted being useful. And then these are the organisations I would like to thank for having funded this research. And finally, I would like to acknowledge the following people that have contributed over the years to these projects, and which I think highly highlights the need for collaboration. And based upon the insistence of my PhD students, we also have a project website called Polymers. And for more information, I can be contacted on this email address. Thank you.
Thank you so much, Petronella Nel. We have some questions for you for the next about 6 minutes. The first is that many people would like to know if your literature review of polymer identification could be shared on the Slack channel, or is the literature review and some of the things that you've shown us, are they on the website that you just showed?
So I essentially, they may not have realized that right near the end, I provided a list of the references. So I'm assuming that this is recorded, and so you would be able to obtain it from the recording. But if there's another way that the organisers would like me to make that information available, or I guess I could add it to our website as well.
Great. So we can talk about that
perhaps to share that. Yes.
Later. It was just the top question that everybody asked.
Okay. Because some of those informations are freely available. So some you have to access by special access, but some are freely available.
Great. The second top question was the IRUG spectral database is extremely useful for those who have access to infrared spectroscopes. Are you using the IR user group shared spectral library? Was one question.
Well, it's more when we evaluated the database. I found it very useful back when I was researching adhesives, because the IRUG website sort of focuses on intervention materials. It may have been updated recently. I know there's plans to update it with more recent spectra, but when we initially evaluated it, found that it wasn't very good in terms of reference plastic polymer samples. So we haven't been strongly referring to it, but I am aware that there's work on developing it.
And then a kind of follow-up question, do you think it would be a good development if IRUG would also share spectra acquired with external reflection, with the module for external reflection?
Yes, because to make the spectral matches, it's best if you do have the reflectance spectra, because the KKT transformed absorbance spectra are subtly different from your normal ATR spectra. So yes, I would agree that that would be a new area that needs to be added.
Great. One innovation already. Check. Is there an existing aged samples database, or is this something that individual teams would need to develop over time?
I think there are various groups that may be in the middle of aging samples. I have in the past aged adhesive samples, and we are in the middle of generating aged samples just with artificial aging methods. But I think we should also be looking to deaccessioned objects that have degraded as another resource of real-time aged samples. But I think we'll find it's important to be collecting that information as well.
Great. Which chemical spot tests did you test for the adhesives in pottery?
Okay, it was things like the cellulose nitrate test, the molish test. I'd have to refer you to the publication. So I'm unfortunately not remembering it off the top of my head, but it was any kind of spot test from Odegaard that was relevant to the reference samples I had. So I'm sorry, that's the extent of what I can say.
No,
and
that's great.
I did find that there was a little bit of ambiguity with an iodine test in differentiating between polyvinyl acetate and acrylics because they have a very similar functional group. But all I have to say is that, look, it led to me, detecting a formulation difference. So chemical spot tests are not all bad.
Great. If you wanted to, you could put the reference, if you have time, onto the Slack channel later after the conference.
Yep. So the reference was provided at the bottom of the slide.
Okay. Sure.
Yeah.
Yeah. All right. Did you try to use all the RI crystals to test the polymers in order to create a larger IR database?
So I've only ever used the diamond ATR because I am in a teaching lab. So I don't want to have heart attacks about the students somehow managing to kill the ATR window, because I saw in the School of Chemistry they had one of the other cheaper windows, and the technician was always panicking about somebody, damaging, because the other ones are just much more fragile. So I know that there are certain specific instances where particular polymers measure better on those other cheaper types of crystal windows, but I've only had experience really with the diamond, and I don't want to have heart attacks by using the other types.
All right, thank you. That's a very good hint. And following up on that hint, we have a comment from Greg Smith, who wrote, "Be careful with resin kit. Accuracy is rather poor," and they identified 17% wrongly labeled and from two different kits, and the inaccuracies were also not the same. So this is a caveat for everyone.
Yeah, so I think there's been several dates of the resin kit where different problems have been discovered. We also found that a lot of our resin kit samples were coated in talc. So we were measuring the talc instead of the polymer and had to first remove that, which might have been used as a release agent or something like that. And yes, that was highlighted by the IRUG meeting that was in Sydney a few years ago.
Great. So I think we're out of time at this point, but I can see from my list of questions that many people are eager to find out more from you. What I would say is that our team will put the rest of the questions in maybe a special questions category that we have yet to create in Slack, and then maybe we can continue this conversation